Okay. The one other thing is we do a lot of in-class assignments. It's not just board sheets where you go up to the board and you're done. You actually do have to record those things on an in-class worksheet. The reason I do that is because I'm trying to make sure that you got everything in class you're supposed to get. So this way I get a record of what you did. It's like really low stakes. It's really hard to mess that up unless you're totally blowing it off. Those have to be turned in. Now, if you're on trip section or you're away or you're ill, you're still responsible for those. You still have the class recordings, so you can catch up on those and then turn them in that next class period. And I think that's the highlights of the syllabus. So I'm going to start with what a differential equation is. I'm going to ask you your background. How many of you were in Jedi math? So you did differential equations in there. And so you weren't in Jedi math, so you had the MA 103. You kind of were doing differential equations in a discrete setting. So a differential equation is an equation. I don't have my nice colors on my PowerPoint, but here's has to have an equal sign. Let me see. It must have a left-hand side and a right-hand side. So this is not a mathematician's precise definition, but must involve a function I'm not going to specify what that function's domain and range is because that's coming, but typically the functions that you think of, and I have t as the independent variable and y of t as the dependent variable. And its derivatives. So it's an equation that involves a function and its potential derivatives. It could have more than one. So if you had the Jedi math class, I'm sure you did second order differential equations, so forth. So that's a engineer's definition. So the solution, what is a solution to a differential equation? What's that going to be? The actual function that satisfies that equation. So I think Dr. Groves introduced herself to you. We're both going to ask you to always check your work by, whenever you have differential equations and you find a solution, to actually verify that solution is going to be a solution to the differential equation. It's a no-brainer. It's a way that you can check your work. So it satisfies the equation. So I'm going to show you some examples in a sec, but I'll pause to make sure everybody's caught up. Okay, you're fast writers. So in the field I work in, everybody that works in the nutrition side physical activity, exercise physiologists and nutrition faculty have to take courses that have differential equations in it, but it goes like this out the door. So they spend a lot of time with data and statistics. And so when I tell them I have a solution to a differential equation, the biggest one that we have is weight loss trajectories. Those things actually confuse them because they are asking for the data and the numbers that go into, where did that come from? And so I've had to explain this to them many, many times because it seems like voodoo. All of a sudden, here's a solution and it has no data. Like I didn't need data to generate the solution. And the one thing I tell them is, well, if you wanted to predict who's going to hit a ball out of the park in baseball, one way you could do that is you could go to a lot of baseball games, collect data on what influences the different factors that would help someone hit a ball out of the park, of the height of the player. You can take all that data, put it together, and then write down regression models that will predict who can actually hit a ball out of the park, what conditions there would be. But another way you could do that is you could start with Newton's second law of motion. Force is equal to mass times acceleration. And I can look at the trajectory of the ball after it's been hit by that force and write down a model. And I didn't need any data to do that. The other way is more fun. You get to go to a lot of baseball games. But in this case, I didn't need any data. So that's kind of how I explain it to them, that there's governing equations that come from physics that allow us to put together a model and a differential equation where I can find that solution. And there's techniques that you're going to learn in here. We can find those solutions and actually come up with predictions that had nothing to do with collecting data and writing down regression models. So I actually think I have even a chart I can bring in here and show you that one that I showed them, because that's something that they find pretty confusing. All right, so this example I'm going to show you right now, since a lot of you had Jedi math, this might seem boring. So simple. I'm not going to put any conditions on A. A belongs to the real numbers. That's a differential equation according to my sloppy engineering style definition. It's an equation. There's an equal sign in it. There's a left-hand side. There's a right-hand side. There's a derivative. There's the original function. And by the way, engineers and physicists are pretty good at putting y of t. Mathematicians drop those. So you'll see me eventually dropping the y and not suppressing the t. I'll just drop it out. Dr. Gross is probably not going to do that, but
It'll depend on how lazy I'm feeling that day.
Those of you who have had Jedi math, that A is what the whole idea of the eigenvalue and eigenvalues telling you everything about the differential equation. Somebody used to tell me, if you know the eigenvalues, you know everything. So if you remember back, did you guys do that in Jedi math? Eigenvalues? A is the eigenvalue. And this canonical example is what drives all of that theory that you learned with eigenvalues, matrices. Like instead of having an A there, you could have a vector with a matrix. So you can have the whole thing there. So this canonical example is actually pretty important. So what do I got here? Here's my function. Here's my derivative of the function. It's on the left-hand side. And the solution is going to be something that satisfies this equation. I say solution because there's a family of solutions. Again, if you had this in Jedi math, this is probably take those notes because we're going to be looking at some theory along the way. So this example is going to be the one that drives everything, as I said before. So we're looking at this differently than Jedi math. I think in Jedi math you plow through and model things and you don't really talk about the whys behind why something is working. C is the arbitrary constant. It's an arbitrary constant. I'm going to prove in a second that this works. Okay, no questions? My classes are usually loud. Right, you guys will have questions soon because I've been told I go fast. A lot of what we do in this class is what I call bookkeeping math. You keep the books and make sure that you did all your calculations correctly. So from your work, on your homework, we need to see the bookkeeping. So if you're going to show that that solution is actually a solution, the claimed solution is a solution, what you're going to do is actually show for me y prime of t is equal to, so that's my proposed solution. Y prime of t is c a e to the at. This comes from chain rule. I'll post my PowerPoint notes. In the PowerPoint notes, I have stuff like that goes over again, like what the chain rule was, in case you forgot how that a comes there. So that's y of t is up here, y prime of t is here. Sub into the formula, the equation. This is y prime. It's y. So just subbed it in. I put a question mark there because I'm directly going to inspect it, which I'm going to do right now. Direct inspection by high school commutative algebra. Things move around, and they're identical, right? And so it works. Okay, so.
Is there a symbol or anything to grab the
Your words. Do finish off with the. So, I don't know in Jedi math also if they went over that in most cases, most things that you write down that are of interesting problems do not have what we call a closed form solution like this. Did they talk about that? Okay, so most things we write down that are interesting to us, like maybe predicting the weather, those models cannot be, you can't write down what we call a closed form solution. So some of what you're learning here at the beginning, it's just how to solve things that are easy. And you might use that sometimes if you have an equation that's complicated and you want to approximate it by something that's simple so that you can solve it and look at that solution and say something about it. But in real life, most things you write down, you can't solve. That becomes apparent. So we're going to look at also what's called qualitative solutions, like qualitative methods, like looking at the differential equation and understanding what happens. Because if we know the derivative, we got a whole class on that. MA 104, Calc 1, you guys took it in high school, most of you took it in high school. So that course is just about understanding a function from its derivative. So we'll use that as well. But I'm tired of talking, so I'm going to send you towards. Don't you hate when the professor actually puts something harder for you to do than they just did on the board? I'm gonna do that right now. And please. They gotta not give you real analysis stuff. No. All right. All right, perfect. Turn pages. I think I have a stapler somewhere, so I'll bring it in. So hang on to these because you're going to be working on it during the week. All right, go ahead and take boards.